Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an Associate Professor in the Department of Electrical and Electronics Engineering. So in today's, we are continuing to discuss on network theorems with AC excitation. So in the previous class, we have discussed the superposition theorem and also we have discussed about the Thevenin's theorem. And in today's class, we will continue to discuss the Thevenin's theorem by taking another little bit complicated circuit than the circuit which we have considered in the previous class. So here in this circuit now we have to draw the Thevenin's equivalent circuit, or we have to find the parameters of the Thevenin's equivalent circuit in between the terminals AA, which A and A dash. So here in between these two terminals we have to find or we have to draw the Thevenin's equivalent circuit. So for that, as we know, for the Thevenin's equivalent circuit consisting of the Thevenin's voltage and Thevenin's resistance, okay, and series with the load resistance. So here the load resistance that we can consider as a the R3, which is the 7 ohms. So here I have just drawn how the Thevenin's voltage, for which circuit we should find the Thevenin's voltage, and also for which circuit we should find the Thevenin's impedance or the Thevenin's resistance or Thevenin's impedance that I have drawn here. So here the first circuit, by using this first circuit, we can find the Thevenin's voltage or the open circuit voltage across the terminals A and A dash. So for that here R1 plus jx1 here, so which means here the Z1 is equal to R1 plus j into xl1, and similarly here the Z2 is equal to R2 minus jxc, and similarly here the Z3 is equal to, of course here jxl2. So which means here R plus jxl1 is here R is equal to 6 plus j into 8, and similarly R2 is 3 minus j into 4, and similarly here Z3, which is equal to J5 ohms. So these are the values that the Z1, Z2 and Z3. Okay. So instead of resistance and the inductive reactance and the capacitive reactance, so simply I have just converted into the impedances. So for this particular circuit, we need to find the Thevenin's voltage, and here for this circuit, we need to find the Thevenin's resistance. So our Thevenin's impedance here. So to find the Thevenin's impedance, as we know, the active elements, either voltage source or the current source, we should replace. The voltage source should be replaced with the short circuit, and the current source should be replaced with the open circuit. So anyway, here we are having only one voltage source, this one, the E1. So that E1 is replaced with the short circuit, and then for this particular circuit, or by using this circuit, we can find the Z Thevenin's. So first let us find the Z Thevenin's. Here first let us find the Z Thevenin's. How to find the Z Thevenin's? Of course here it is very easy, because here the Z1 and Z2 are in parallel, so that here and the parallel combination of Z1 Z2 is in series with the Z3, then the equivalent resistance or the equivalent impedance here, the Z Thevenin's, which is equal to Z3 plus here Z1 and Z2 are in parallel, so Z1 Z2 by Z1 plus Z2. Then substitute these values here. Here Z3 is the J5 ohms plus here Z1 is of course I have just converted these rectangular form into polar form. So directly here I am writing the Z1 Z2 values in polar form. So here the Z1 value is 10 ohms at an angle of 53.13 degrees, and similarly the Z2 is 5 ohms at an angle of minus 53.13 degrees by, of course here because it is plus, so that's why I'm again writing in terms of the rectangular form only, which means A plus JB. So here 6 ohms plus J into 8 ohms plus again Z2 is 3 ohms minus J into 4 ohms. Then if you simplify this, then you will get the finally the Z Thevenins, which is equal to 4.64 ohms plus Z 2.94 ohms. So which again it can be converted into the polar form. Then if you convert this value into the polar form, then you will get the value as 5.49 ohms at an angle of 32.36 degrees. So already we know how to convert the polar into rectangular and rectangular into polar form. Okay, so that I think no need to discuss again here. So this is how now we have calculated the Z Thevenin's value. Then now we are going to find what is that the E Thevenin's value, right? So here E Thevenin's is nothing but it is in between the terminal A and A dash. So to find the E Thevenin's in between the A and A dash, as you can see here, which means the voltage across A and A dash is nothing but the voltage across the Z2 impedance. Why? Because here the Z3 which is connected to the open circuit, okay, so that's why the current flowing through the open circuit is 0, so that here the current flowing through these Z3s becomes 0. So that's why here the voltage across A and A dash is nothing but the voltage across the Z2. Then here the voltage across the Z2, which is nothing but, which means here now we should consider only this loop. Okay, so here this is the total voltage that we know, and now we can apply the voltage division rule to find the voltage across the Z2. So which is the voltage across the Z2 is nothing but E Thevenin's. So here E Thevenin's, which is equal to the total voltage is here it is E1 into, and where we need to find across Z2, so that's why here Z2 by Z1 plus Z2. Then substitute the values of E, Z1 and Z2 in this equation. So here the value of the E is the 10 volts at an angle of 0 degrees into, here the value of the Z2 is 5 ohms at an angle of minus 53.13 degrees by, here Z1 Z2 is, of course just here I am writing the Z1 plus Z2 value because previously we have calculated the Z1 plus Z2 value. So here it is Z1 plus Z2 value is 9.85 ohms at an angle of 23.96 degrees. Then if you simplify this, then you will get the E Thevenin's value, which is E Thevenin's equal to 5.08 volts at an angle of minus 77.09 degrees. So now we got the value of E Thevenin's as well as Z Thevenin's. Okay. Then the Thevenin's equivalent circuit is, of course, here like this, which is E Thevenin's. Okay. This E Thevenin's is in series with the Z Thevenin's. This is Z Thevenin's. Okay. And again the load resistor is there because here we are finding in between A and A dash. Okay. So here in between A and A dash, there is another resistor. Okay. So which is R3. So which is the value is 7 ohms. And also there is another resistor. Okay. So which is E2. Then this is now the what is the Thevenin's equivalent circuit. Thevenin's equivalent circuit. Right. So now let us substitute the values. Right. E Thevenin's just now we have calculated, which is 5.08 volts at an angle of minus 77.09 degrees. Okay. And similarly here the Z Thevenin's value is 4.64 ohms plus Z 2.94 ohms, and R3 value, this is the load resistance, which is 7 ohms. This is given in the problem, and again E2, that is 30 volts at an angle of 15 degrees. Okay, so of course if these Z Thevenin's can be divided into what is that rectangular form, so which is R plus here, because Z 2.94 means here it is the reactance, which means R plus JXL. So here R and JXL. So here R is equal to 4.64, which is the real term, and the imaginary term 2.94 is the inductive reactance value. Then this is now the Thevenin's equivalent circuit. So here by using this Thevenin's equal, why we need the Thevenin's equivalent circuit? Now you can find the current flowing through these R3 resistor by applying, of course you just find again the total impedance, which is 4 plus 7, here it is 11. So then here the total impedance, here it is Z total, let us consider, here it is 4 plus 64 plus 2.94 plus Z, sorry, 4.64 plus 7 plus Z 2.94 ohms. So this will become 11.64 plus Z 2.94 ohms. Right. Now again add these two also. Okay, because here these two are in series. The what is that? The voltage sources. Okay. Then here the total current I is equal to ETH plus E2 by ZT. Then you will get the total current I which is flowing through this resistor R3. So this is how we can find the current flowing through the load resistor by using the Thevenin's theorem. Next we will discuss about the Norton's theorem. So here the Norton's theorem is almost similar with the Thevenin's theorem. The only difference here it is because here the Norton's theorem, okay, to apply the Norton's theorem, first we will convert the old circuit into the Norton's equivalent circuit. So here the Norton's equivalent circuit is little bit different than the Thevenin's equivalent circuit, because in the Thevenin's, of course, here also there is a Norton current instead of the Thevenin's voltage. There is a Norton current that we need to find, and here the similarly like the Thevenin's impedance, here also we will find the Norton's impedance. Okay, the procedure to find the Norton's impedance and the Thevenin's impedance both are same. So only the difference is there we calculated the Thevenin's voltage, which is nothing but the open circuit voltage across the load terminals. But here we will find the short circuit current across the load terminals, because here the load is replaced with the short circuit, and find the current flowing through that short circuit, which is called the Norton's current. Okay, then the equivalent circuit for this is the same way. Okay, so here the Norton's current, right? Okay, in parallel with this is IN, let us consider, and here it is ZN, that is the Norton's what is that impedance, and this is the resistance RL. So now this is the Norton's equivalent circuit, which means for this given circuit, okay, we need to find or we need to draw the Norton's equivalent circuit for a network by connecting the external resistance of 6 ohms. So which means here the 6 ohms resistor is, let us consider as a RL. So we need to find the Norton's what is that current across these two terminals, as well as the Norton's impedance across these two terminals. So here the same way, here the all the what is that resistors and the reactances are replaced with the impedance. So here the Z1 which is equal to, so here Z1 which is equal to R1 plus JXL, and Z2 which is equal to minus JXC. So which is nothing but here R it is 3 ohms plus here JXL is equal to 4 ohms. And similarly here XC is equal to minus J 5 ohms. Right? So by using this circuit, of course here also the procedure to find the Norton's impedance is same as like the Thevenin's impedance. So that's why here when we are finding the Norton's impedance, just replace all the active sources as a open circuit or the short circuit. If it is a voltage source, then we should replace it with the short circuit, and if it is a current source, then we should replace it with the open circuit. Now of course anyway here we are having only the voltage source, so that's why this voltage source is replaced with the short circuit. Then we will find the total or equivalent impedance across these two terminals for this particular circuit. Then in the second case, when coming to the Norton's current, so we should replace the load resistance with the short circuit. So that's why here the 6 ohms is replaced with the short circuit across these two terminals. Now we need to find the current flowing through this short circuit for this particular circuit. Then we will get IN. Then substitute ZN and IN in the equivalent circuit, so that you can find the actual current flowing through the 6 ohms resistor by using this Norton's theorem. Right? Now first let us find what is that the Zn, which is the Norton's impedance, right? So here it is very simple, because the circuit is also very simple, because here as you can see Z1 Z2 are in parallel. So here the Zn which is equal to Z1 Z2 by Z1 plus Z2. So substitute the values of Z1, Z2. Then here the Z1 value is, of course, which is 3 ohms plus 4, what is that? Yeah, J4 ohms into here Z2 value is minus JXC, right? So minus JXC value is 5 ohms by here Z1 is again 3 ohms plus J4 ohms plus of course here minus of J 5 ohms. So if you simplify this, then you will get the Zn value as 7.50 ohms minus J 2.50 ohms. So now this is the value of the Zn, which is the Norton's impedance, the equivalent Norton's impedance. This is Zn. Now we need to find the In value. Okay, so for that here we need to find first of all, because here for this particular circuit we can apply the current division rule. So by applying the current division rule, you can find easily the current flowing through the short circuit, because here let us consider here I1 is the total current, and this total current is dividing into some of the current will flowing through the Z2 and some of the current will flowing through the short circuit, right? So to find here the In value, so In is equal to directly we can find In is equal to, so which is nothing but In, it is nothing but what is that, the I1, which is equal to E by Z1. So what is the value of E that they have given in the problem, which is 20 volts at an angle of 0 degrees by here Z1 is, if you convert into the polar form, then 5 ohms at an angle of 53.13, okay, 53.13, which is equal to 4 amperes at an angle of minus 53.13. So here then the Norton's current is 4 amperes at an angle of minus 53.13. Now substitute these In value and as well as the Zn value in the equivalent circuit of the Norton's theorem, okay, or the Norton's equivalent circuit. So here this is the Norton's current and this is the Norton's impedance, and these two must be connected in parallel, or these combination must be connected in parallel with the load resistance. So here you can observe the major difference between the Norton's theorem and Thevenin's theorem. So only the difference is, or first let us discuss the common points between the Norton's and Thevenin's theorem. So in the Norton's and Thevenin's theorem, the common point is, of course, there also we need to convert the total circuit into the Thevenin's equivalent circuit, and here also we should convert the total circuit into Norton's equivalent circuit. And the difference between the Norton's equivalent circuit and Thevenin's equivalent circuit is only in the Thevenin's equivalent circuit we are having the variable as V Thevenin's and Z Thevenin's and as well as the load, and all these three variables are these three components are connected in series. But when coming to the Norton's theorem, of course here also we will be having the three variables, but here only the difference is, instead of having the V Thevenin's, here we are having the In Norton's, because there the Thevenin's voltage, here it is the Norton's current, and the Thevenin's voltage is also called as the open circuit voltage, and here the Norton's current is also called as the short circuit current. So because we are replacing the load as a open circuit, okay, and in between those two terminals we will find the voltage, so that's why that is called the open circuit voltage or the Thevenin's voltage. But in case of Norton's theorem, so here we are replacing the load resistance as a short circuit and we are finding the current through the short circuit, so that's why this is also called as a short circuit current or the Norton's current. And when coming to the equivalent circuit of the Norton's and as well as the Thevenin circuit, so in the Thevenin circuit, those three variables are the three components like V Thevenin's, R Thevenin's and the RL load resistance are connected in series. But where coming to the Norton's equivalent circuit, here the In, which is the Norton's current, and Zn, which is the Norton's impedance, and RL, again the same load resistor, are connected in parallel. Okay, so that is the difference between the Thevenin's theorem and the Norton's theorem. Now let us consider another problem. For this particular problem, again we need to draw the Norton's equivalent circuit. Of course, here this is a little complicated circuit than the circuit which we are considering previously. So here we need to find or we need to draw the equivalent circuit when here the 7 ohms capacitive reactance as a load resistance, let us consider. So then here also again we need to find what is that, we should replace this load resistor which we are considering, or the external resistor which we are considering, with open circuit to find the Z Thevenins, the Z Nortons, and as well as replace it with a short circuit to find the I Nortons. So here by using this circuit, because of course here the only difference between the previous circuit and this circuit is previously it is having the voltage source and here now it is having the current source. Okay, so that's why I have considered the different problem. Okay, so here first of all let us draw the circuit to find the Norton's impedance. So for that here first of all we should know where we need to find the Norton's impedance. Okay, as we know, as usually across the load terminals we need to find the Norton's impedance. So by replacing the just eliminate that load terminal, and across those load terminal we need to find the Norton's impedance. And again then the procedure to find the Norton's impedance is we should replace the active elements which are voltage or current sources. So of course here it is having only the one current source, and this current source can be replaced with the open circuit. If it is a voltage source, then the voltage source must be replaced with a short circuit, right? Of course, anyway, here we are having one current source, so that current source is replaced with the open circuit. So for this particular circuit, now we need to find the total impedance across these two terminals, which is the Z Nortons. Then when coming to the Norton's current, of course, we should replace these again the load resistance with the short circuit, and we need to find the current flowing through this short circuit, then which is the I Nortons, right? So first of all, let us find the Z Nortons. Okay, so here to find the Z Nortons, okay, so we need to identify what are the two resistors which are connected in series and what are the two resistors which are connected in parallel. So anyway, here as you can see, here the Z1 and Z2 are connected in series, and the combination of the Z1 and Z2 are connected in parallel with Z3, right? Because let me redraw this circuit. Okay, so here of course anyway it is open circuit, so that's why here you will be having only Z1, right? This is Z1, okay, and this is Z2. Okay, this is Z2, and this Z1 and Z2, because here this is Z1 and Z2. Okay, so here this is the point, and here this is the point. Okay, anyway we need to find in between these two terminals, okay, these 2 points, right? So that's why here let us consider these 3. This is the Z3. So we need to find the voltage across the Z3. The impedance across the Z3. So that's why here, okay, so here we need to find across these two terminals. Okay, so which means here these two are in series. Okay, and this terminal is again the same way. Okay, so let me just connect this terminal to this. Okay, and then find across these two terminals. So which means here these two are in series, and this series combination is parallel with the Z3. So that's why here then let me write the equation for the the Z Nortons, which is, so here the Zn, which is equal, here Z1 and Z2 are in series and this combination is parallel with Z3. So therefore Z3 into Z1 plus Z2 by here Z3 plus Z1 plus Z2. Then substitute these values here. So here then the Z3 value is 5 ohms at an angle of 90 degrees, and the Z1 plus Z2, of course the value Z1 plus Z2 value, okay, directly here I am writing, that is 5 ohms at an angle of minus 53.13 degrees by here the Z3 value is again, what is the Z3 value? Of course the same value, here it is 5, or just because here it is addition, so I am just writing in a rectangular form. So J5 into 3 ohms minus J4 ohms. So if you simplify this, then you will get here it is 25 ohms at an angle of 36.87 degrees by, and this is because J5 ohms and J4 ohms, so that's why here 3, of course here 5 minus 4 is plus 1, so that's why place J1 ohm. Then finally, here the Z Nortons, which is the Z Nortons, the Zn, which is equal to 7 point, if you convert, if you simplify and convert into the rectangular form, then 7.50 ohms plus Z 2.50 ohms. So now this is the Z Norton's value. Right? How we can have converted this one into the simple circuit, which means here the Z2 and Z1. So these two are in series. Okay, and the series combination is in parallel with Z3. So here in these two terminals, we need to find what is that? The Zn, that is the Z Nortons. Right? Okay, fine. Now we need to find the current flowing through this IN. So how to find then the current flowing through this IN? So now we know the total current. Okay, so that is I is equal to 3 amperes. Then here IN or I, okay, which is equal to IN, okay, which is equal to I1, which is equal to the, what is the total current is high, okay, I, into the opposite resistance, here it is Z1, okay, because in this the total current we are flowing, okay, just we are considering this as a total, what is that circuit. So here I into the opposite resistor is Z1 by Z1 plus Z2, right? So if you simplify this, then here I is 2 ohms at an angle of what is that, minus, no, here Z1 is 2 ohms and J 4 ohms, okay, and I is here 3 amperes at an angle of 0 by again the Z1 is Z1 plus Z2. If you simplify, then here it is 3 ohms minus J 4 ohms. So if you simplify this, then you will get the Norton's current IN, which is equal to 2.68 ohms. Sorry, this is current, okay, 2.68 amperes at an angle of minus 10.3 degrees. So this is the Norton's current, I Norton's, right? So then just what is that, replace or substitute the IN value and Zn value in the equivalent circuit. Okay, so this is the equivalent circuit. Of course, here Zn is 7.50 ohms plus J 2.50. So we can divide this impedance into resistance plus the, what is that, inductive reactance. Okay, that is what is that, R plus JXL. Okay, then the circuit will become like this. So this is how we can what is that, apply the Norton's theorem as well as the Thevenin's theorem for the given AC circuits. Of course, the procedure is same, only the difference is, because here, of course, because in case of DC circuits, we will be having only the resistors, but here we are having the capacitive reactance and as well as the inductive reactance. Okay, so in this case, we are using, because here the phase angle is also a point that we need to consider, because in the DC circuits it is not like that, just the normal addition, because here it is the vector addition. So that is the only difference between the AC and DC circuits, right? So in the next class we will discuss the remaining theorems. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.